Okay, so welcome to our play posit on electric potential. And the first question I have for you is, here I have three charges in between two parallel plates. I've drawn in the electric field, and my question for you is, which charge has the most potential energy? If you said this leftmost charge, you are correct. This one has the most potential energy because think about where a positive charge wants to be. It wants to be far away from positive and close to negative. So if I let this one go, it's going to go slam down here and gain a whole bunch of kinetic energy, gain a lot of velocity along the way. This one is going to have some potential energy, but remember, we always think about potential energy in relation to how much energy you can get back out of the system. So in this case, this one doesn't move as far. You might always remember that that work that's done by forces is force times distance. This doesn't have as much distance to cover, and therefore it gets less energy. This third one doesn't actually get to move at all when you let it go. It's already where it wants to be, and so it's not really going to move. It's not going to pick up any energy. So we can kind of think about this side as having a high amount of potential energy, and this side is having a low amount of potential energy. All right, so today we are talking a little bit about electric potential, and what's interesting / confusing here is we want to be able to distinguish this concept of electric potential energy. And when we talk about electric potential energy, it is energy. We're going to measure it in joules, like we measure all of our energy. And we want to distinguish it, though, from this other closely related but different concept, which we're going to call electric potential. Not potential energy, just potential. And we measure this one in volts. And it is sometimes also called voltage. So these two are very closely related. Volts are a measure of potential energy, but they're not quite the same. So we're going to start by calculating the potential energy of sets of charges, talk about what the heck this difference is, potential energy versus potential, do a little bit of calculation with that, and then kind of start to get into this question at the very end of what the heck does voltage mean? And that's going to carry us into our next part this coming week on equipotential lines and electric fields, and then from there on into circuits. You'll notice I've highlighted a couple equations. These are straight off your formula sheet, and these are some of the equations we're going to look at over the next week or so. All right, so let's talk a little bit about potential energy of charges, right? If let's say I take two charges, Q1 and Q2, and I'm going to just, for the sake of argument, drive a little spike through Q1 and fix it in place so it can't move. I'm going to hold Q1 stationary. I'm going to bring Q2 here, and then I'm going to let it go. And when I let it go, these two things are going to repel, and it's going to go and fly off forever. It's actually going to fly off forever, because if you think about it, that electric force goes as 1 over r squared, and 1 over r squared never, ever, ever becomes 0. It just kind of diminishes and diminishes. So Q2 will go forever. And I want to ask, how much energy does Q2 end up with? Because think about it, if it ends up with some amount of kinetic energy at the end, that's how much potential energy it had to have to start with. So we're going to calculate the work done by this electrostatic force. You might remember, of course, that the force on this thing, the electric force on this is going to be that 1 over 4 pi epsilon 0, that K constant, times Q1 times Q2, all over r squared. In this case, instead of using r squared, I actually want to use x squared, because you'll notice I've put everything on the x-axis. So x is just the distance between them. So let me set up this little integral, because in general, work is an integral. Well, the force that's being applied here is going to be 1 over 4 pi epsilon naught, Q1, Q2, all over x squared with respect to x. And then, of course, where do I start? I start at x equals r. And I go, it's an improper integral, I go all the way out to infinity. It never stops moving. It goes as far out as we want. All right, so let's do this integral real quick. Well, a bunch of these things are constants. Q1 and Q2 are constants. 4 pi epsilon 0, those are constants. So I'm going to pull those out to the front. Q1, Q2 over 4 pi epsilon naught. And then I have this integral of 1 over x squared. And another way to write 1 over x squared is, of course, x to the negative 2. So we might look at this and say, aha, I know what the integral of x to the negative 2 is. I know it happens to be negative x to the negative 1. So negative 1 over x is the integral there. So I'm going to integrate that from r all the way to infinity. I still have q1, q2 over 4 pi epsilon naught. If I plug in infinity, well, let's see, 1 over basically something that goes to infinity ends up as 0, minus negative 1 over r. So I end up with a plus here. And what I get in the end is that the energy associated with this configuration is 1 over 4 pi epsilon naught q1, q2, just over r, not over r squared, just over r. And this might seem familiar to you. This is going to look an awful lot like gravity, right? For gravity, our force was g m1 m2 over r squared. And our potential energy for gravity was negative g m1 m2 just over r. So there is a similarity here. There is one big difference, though, which is that for gravity, our potential energy was always negative. And for this, it's not always negative. So let's do a little bit more inspection here. So a couple of things to note. First of all, our potential energy is 0. Approaches 0 as r approaches infinity. So we always have to pick our place. Where do we put the 0 of potential energy? So we always, for these kinds of potentials, we always put 0 at infinity. We always put 0 as being infinitely far away from the system, not involved at all. It is important to note that where our force was a vector, energy, as energy always is a scalar. And this actually makes it much, much easier to calculate in a variety of scenarios. And I also want to, let's just take a look at these graphs, right? What's important to note is that if we have like charges, then Q1, Q2, is either going to be plus times plus, or it's going to be minus times minus, in which case our energy is positive. And one way to interpret this is, you might remember when we talked briefly about potential energy graphs, is that you can read potential energy graphs like a hill and figure out which way things are going to want to move. If I put an object on this hill, right, it's going to want to roll down and away, which is to say that like charges repel each other. Like charges repel each other. If I have unlike charges, on the other hand, if I have a plus minus or a minus times a plus, I end up with a negative total potential energy. And if I put an object there, it wants to fall in. So this is another way of saying that these potential energies also confirm for us the fact that like charges repel and unlike charges attract. Okay. So here's an example, and I wanted to take a second to work this out. What is the total potential energy of this arrangement of charges? They are in an equilateral triangle. We got plus Q, and minus Q. So take a moment and see if you can figure that out. All right, well, I'm here to tell you the solution here. So let's take a look at some of our charges here. So we've got these two charges together, plus Q and plus Q. Well, let's give them some numbers. This is 1, this is 2, and this is 3. So the potential energy associated with 1 and 2 is just going to be 1 over 4 pi epsilon 0 times, well, they're both Q, so we end up with Q squared all over L. And remember, it's not over L squared, it's just over L. It's also important to note that the potential energy associated with 2 and 3 is going to be 1 over 4 pi epsilon 0 times negative Q squared, because it's going to be plus Q times negative Q, all over L. And that the energy associated with 1 and 3 is actually just the same as this. So how do I find my total energy? Well, it's going to be the sum of all of those. So I'm going to get, 1 over 4 pi epsilon naught. I'm going to get kind of a plus Q squared over L, and then minus 2Q squared over L, because, again, I've got 1 of these and 2 of these. So my total net potential energy is going to be negative 1 over 4 pi epsilon 0 Q squared. over L. So my net potential energy here is negative, which kind of means that, one way to think about it is that these two charges, they want to get attracted in. Our system really wants to pull together as negative energy. If it has positive energy, our system really wants to kind of fall apart. If our energy is 0, it's pretty stable. All right, excellent. Now, what if I asked you, how much potential energy would we have if I put a little test charge right in the middle? And I want to remind you that this is kind of a shift that we have made already. This is a shift in perspective that we have made already in E&M. Because your first instinct might be to be like, well, Mr. Bates, how can I calculate the potential energy here? I don't know what's there. I don't know what charge is there. And I want to remind you that we can say, well, I don't know what charge is there. I don't know what charge is there. But I know that if I did know what charge is there, and we'll call that test charge big Q, I could calculate it by being like, okay, well, 1 over 4 pi epsilon 0 times little q big Q all over, well, I'd have to figure out what this distance is. We're just going to call that distance d for now, so we don't have to work it out, plus some other stuff that's going to depend on this. There's going to be a minus term in here for our lower one. And what I want you to notice is that this big Q pops up, is going to pop up in each term. And so I could kind of say, well, I have a bunch of stuff that doesn't actually depend on my test charge. I have a bunch of stuff that just depends on my arrangement of charges, on these source charges. And this is very similar to asking ourselves, what's the electric field at a point? We don't necessarily know what force is going to be felt, but I can say, hey, if I've got an arrangement of charges, just like in my problem, plus Q, and minus Q, I can ask, hey, what's the electric field at that point without necessarily knowing what's at that point. So we want to kind of change our language from this exact potential energy of arrangements of charges to, well, what would the potential energy be if I put something there? Because we can say things about it. Even if I don't know what Q is, I can still look at this and say to myself, well, its potential energy might be relatively high because it's pretty close to two positive charges, and it's going to want to fall towards this negative charge, so it's going to get pushed this way. It may have a relatively large amount of potential energy. If I moved it really close to one of my charges, its potential energy would probably go up because at this point I have to push it. I have to put in some work to get there, so it must have a higher potential energy.